Continuing from the last lecture, we are now going to predict the convective layer thickness and temperature with respect to time. Right? So in the last lecture, we understood how this convective layer that actually starts forming from the bottom surface starts becoming thicker and thicker with time, right? And that is why the H value, that is the thickness of the convective layer, becomes thicker with time or becomes larger with time. At the same time, the temperature of that convective layer, that also rises with time, right? And while we assume that originally there is a stratification in the system or in the atmosphere, but with convection this stratification goes away and each convective layer attains a constant temperature at that particular time. Okay, so we are going to predict the value of H and capital T with respect to small t, that is time. So convective layer depth H and temperature capital T. Okay, so this is what we are going to predict. So let's assume that this is the bottom surface, right, and this is the atmosphere. Okay, and here the original temperature in the system was increasing from T naught at the bottom slowly towards a greater value because of stratification. Okay, so that is our temperature profile. And if we assume that this is an axis, for instance, this is the z-axis, in this side we are defining the temperature axis, right, for the atmosphere. So originally this will be your T naught, that is the surface temperature or the temperature of the air near the surface, right? And this is your Ti, which is a function of z originally, right? And now what we assume is, because we are sort of supplying heat at the bottom, right, there is heat that is going from the surface to the fluid because of the sunrise, as we discussed in the last lecture, right? The surface first gets heated up and that starts supplying heat into the air, and we assume that is Q, that is heat flux per unit area per unit time. Okay, and with time, let's assume the convective layer that is slowly becoming thicker. So at certain time, let's say T, this becomes this thick. Okay, so this is now, let's say H, which is a function of time. So this is the convective layer. Okay, that is the convective layer at time T. Okay, and let's assume this has temperature with temperature T of T. Okay, capital T, and this capital T has to be greater than the original temperature that it had at that particular location. So we will assume that the temperature of this layer has risen, and that is something like this. Okay, so this is T of T for that particular layer at that particular time. Okay, so what you see in the red is the original temperature, and what you see in the orange is the new temperature for that layer. And now let's assume that this H that increases slowly if at later time t, if it has gone further, in that case this will be your this will be your h at time t, and your temperature will look something like this. Okay, so these h and t both are getting updated continuously because of convection within that zone. Okay, so this one can be defined as convective layer at a later time. All right, so now we are trying to predict this value of h as a function of t, and also t as a function of capital T as a function of time t. Okay, so let's first define this ti that we have, and we briefly discussed that in the last lecture, that the initial temperature Ti is defined as T naught plus gamma Z. Okay, where T naught is the temperature of air at the surface, and that is at Z equal to 0. Okay, before convection begins. Okay, so we assume T naught equal to T infinity, that is our reference temperature for this case. Okay, and sigma is the stratification slope as we have discussed. All right, so this is something we already discussed in the last lecture. And now let's assume after this convective layer has attained a thickness of a small h, right, for this green region for instance, right, this layer we define. Okay, so I think I will erase the other one so that it's not confusing. We are it will be sure that we are just talking about one h value rather than two h value. Okay, so that green what you see here is the convective layer. Okay, and temperature at Z equal to h before convection, okay, should be at Ti equal to Z equal to h, so that should simply be T naught plus sigma h. Okay, so that is the temperature before convection started. Okay, and now so that is we are considering that in red, so let's just put that in red so that we are consistent. Okay, and now we are considering another temperature at Z equal to h after convection. Okay, so that is at the top of the convective layer. Top of convective layer after convection, that is basically this value, right, that point, whereas previous value that we considered was this one. Okay, so these are two different temperatures we have, and what you see here is the delta T, right, there is some delta T here, that is the change in temperature. So we are trying to find these two values. So that should be T at Z equal to h is the new temperature, right, and that must be equal to Ti plus delta T. Okay, so that delta T that you have here is the rise in temperature due to convection. Okay, and we can in fact be very clear that this is Ti at Z equal to H plus delta T. Okay, because Ti has different values. Okay, so that actually gives us the delta T, that is T at Z equal to H minus Ti at Z equal to H. Okay, where Ti at Z equal to H is T naught minus, sorry, plus sigma H. So delta T becomes this, or in other words, delta T is simply T minus T naught minus sigma H. Right, so this is the rise in temperature at that particular point at top of the convective layer that has thickness H, right? And now if we consider that thickness itself is a function of Z, so we can actually also write it as at any time t, delta T can be defined as T minus T naught minus sigma Z, okay, as a function of Z. So this is something we are going to use. So now we have defined delta T, that is the rise in temperature for that particular location H, but that location H itself is changing in time, right? And that is why we are defining this as a function of Z here. So I will also write here this as function of Z. Okay, so now we have got the delta T, so we can find the total heat that this fluid layer has consumed. Okay, so we will now do the heat balance for the convective layer, so that we can do so by doing 0 to H. Okay, so we are doing for the convective layer, this will be rho Cp delta T dz equal to Q time T 0 to time T. Okay, so Q is the heat flux that is going per unit area. Remember that thing, that heat flux here is per unit area, right, and per unit time. And that is why this heat in the left hand side that we are calculating, we are integrating it only with respect to Z, not for the area, because this is per unit area. Whereas this total heat, if you find rho Cp delta T, that gives you the heat per unit volume, and we are just multiplying with dz so that we get rid of the per unit area term. All right, so now here we put rho Cp in delta T, because we are integrating it with respect to Z, although we know that at final point the delta T is this, but we are integrating it. That's why here the temperature, this value should be sigma Z dz equal to Qt 0 to T. Okay, where T here is obviously measured from the start of convection. All right, so now here we are going to make it little simplified, because we know that our rho is also changing with time, right? Because as fluid gets heated up, your rho value will also change, but we will apply using Boussinesq approximation. We'll consider rho to be equal to rho naught, which is actually our reference density. And why we are doing it? because we assume that convection is happening, but the change in temperature, or sorry, the change in density due to temperature is still very small, that is less than 10% value, right, instead of having a very large value. And that is why the effects of density variation is considered only when it is multiplied with the gravity, right. And in this case there is no gravity, and that's why we can assume it to be constant, so that it's we can take it outside the derivative, and also its effects its variation with time is not significant for finding the heat value, okay, heat flux value. And that is why this equation becomes rho Cp T minus T naught, where T is a function of time. So this, let's first write it as 0 to h T minus T naught minus gamma z dz is equal to qt 0 to t, right. So this is what we have got, and here we have to use rho naught as we already discussed it, okay. And now we have to remember that this t that we are considering, capital T, it's a function of time, but it is dependent for this convective layer, which is 0 to h, right. T is constant, this is a constant value which is only dependent on time, and that is why T can be considered constant. And if you integrate it, this will give you T minus T naught z, that goes from 0 to h, minus sigma z square over 2, that goes from 0 to h, and q over time 0 to t, okay. So this will give us rho naught Cp T minus T naught h minus sigma h square over 2 0 to t qt, okay. So this relation we have got now, let's call it equation number 1. Equation 1 gives a relation between h as a function of t and t as a function of t, right. So convective layer thickness and convective layer temperature. But now we have got just one equation, whereas we have these two parameters, and that is why we must now find another equation that defines that relates h and t, so that we can find h and t separately. Okay, so for that, to find the other parameter, we will perform potential energy analysis. So we will now find potential energy of the fluid layer before convection, right. And this is something we did also in case of shear mixing, if you remember. So we are going to do a similar analysis, and we will call it potential energy I, which is basically we are doing at t equal to 0 when your temperature is just the stratified temperature, right. And here we are trying to find potential energy per unit horizontal area, okay. So and that is why this will give us 0 to h rho g z dz, okay. So whenever we use rho g z as the potential energy, that gives us per unit volume, whereas we are trying to find it for complete layer from 0 to h, but we are trying to do it for per unit area, and that's why we still have rho g z, and then it is integrated with dz from 0 to h, okay. So in this case, now we cannot apply Boussinesq approximation because there is g multiplied, and that is why we have to consider rho as a function of z as well as a function of time. Okay, so here Boussinesq approximation is not applied, okay, because gravity is multiplied there. Okay, so here we can write the density in form of temperature. If you remember the equation of a state that we have discussed, that will tell you that rho is rho naught 1 minus gamma T minus T naught Gz dz. Okay, so if you go back, you will find that the rho is defined as rho naught 1 minus gamma T minus T naught. So this is the equation of a state for temperature, where rho naught is the reference density, right, at T naught, which is the reference temperature. In gamma here is the thermal expansion coefficient, right? This equation we have discussed in the past, and that's why I'm not going into further detail, but we can use this equation straightforward. All right, so now what do we get here? It goes as, so we are trying to calculate Pi, that is the potential energy that we had originally, and here your rho naught is a constant now, right? So we can take the rho naught out and g also out, and what do we get here is 1 minus gamma T minus T naught Z dz. Okay, where here, remember, this we are considering before convection begins, and that is why T here is a function of Z, and that is defined as T naught plus gamma Z, right? So that is this temperature, T naught plus gamma, where gamma here is the large gamma, not a small gamma, and that is why also instead of just using T, we should use Ti here. So this will convert into, and we can also write this as Ti. So this becomes rho naught G 0 to H 1 minus gamma, and Ti minus T naught is capital gamma Z dz, right? That Ti minus T naught is coming from what we just wrote at the right. And so what do we get here is rho naught G Z square by 2 0 to H minus gamma, small gamma, capital gamma, Z cube by 3 goes from 0 to H. Okay, so that gives us rho naught G H square over 2 minus gamma, capital gamma, H cube over 3. Okay, so this is our potential energy for layer 0 to H before convection. Okay, now for the same layer after convection, we can find the potential energy. Let's call it potential energy final, right? So potential energy of the convective layer H at time t. Okay, so now let's call it PEF, that is our potential energy once the convection has reached that depth PF, and we can use the same concept, and this is again per unit horizontal area. Okay, so this potential energy is also per unit horizontal area. And here again we can use the same formula that we just used, so that will be rho g z dz. All right, and here again we can use the same equation of a state for the density and other terms. So let's call it PEF. That will give us 0 to h, where rho will become rho naught 1 minus gamma T minus T naught G Z dz. Okay. And now you have to note that this T that we have here, this T is a function of time and is constant for the convective layer, right? And that is why this is not function of Z for that particular convective layer when we are trying to integrate it from 0 to h. And that is why this can simply be written as 0 rho naught g comes out, and the whole thing actually comes out because gamma is a constant, this T is a constant which is a function of time, T naught is a constant, and we are left with Z dz 0 to h. Okay, so that is very straightforward. This capital T is a constant is a variable in time, but for that convective layer which goes from 0 to h, it's a constant, right? So it's not a function of Z for that particular layer. So this gives us 1 minus gamma T minus T naught h square over 2, right? That is what we will get. So this is our PEF. Okay, so that is the potential energy final, whereas we have already calculated potential energy initial before convection and potential energy final. So here what happens is we are now going to make an assumption that the kinetic energy in the system obtained due to convection is extremely small, okay, such that the potential energy remains conserved. Okay, so this is something that in fact is not just an assumption, this is verified. But for this lecture we will assume this as an assumption because we are not really proving the verification whether the kinetic energy in the system is extremely small or not, or the change in kinetic energy is extremely small or not. And that is why whatever potential energy we had in the beginning should be same later on, as there is no conversion from potential energy to kinetic energy, right? So conversion is 0 as there is no generation of kinetic energy, and that is why we can assume that PE final is same as PE initial, right? Which actually means that delta PE is 0. There is no change in potential energy because delta kinetic energy is 0. Okay, there is no change in kinetic energy, that means there is no change in potential energy, and that is why PF is equal to PEI. That happens because there is just a rearrangement of all the fluids, but still effectively there is no change in these two values, and that is why we can actually relate this term, which is basically potential PEF with PEI, that is this one, right? And here you see that this is same as that one, so that cancels, and we can make some more simplification here. 1 minus gamma t minus t naught h square over 2. Here also we can take the h square over 2 outside, so this becomes gamma sigma, so this becomes 2 over 3h, right? So now this h square also cancels with this one, and once that cancels, this one will also cancel with that one. All right, and that is why what we will eventually get is gamma t minus t naught is 2 gamma large gamma h over 3. So this gamma again cancels with this small gamma, and we are finally left with t minus t naught equal to 2 over 3 large gamma times h, right? So this is our equation number 2 that we wanted, and this one also relates t of t with h of t, right? So now we have got two equations on capital T and h of t, right? So equation 1 is here, which now we can copy. Okay, so this is equation number 1, and that's equation number 2, right? And you can see both of them have this t minus t naught term, which we can now use. So what we will do, we will put rho Cp here. T minus t naught can simply be written as 2 by 3 gamma h minus gamma h square over 2 is equal to q times t 0 to t, and here we get rho naught Cp, gamma comes out. It seems something we are missing. Yeah, so there should be h square here. So h square also comes out, and it becomes 2 by 3 minus 1 by 2. So that will become 1 by 6. All right, so now what do we get here is h should be equal to 6 times qt 0 to time t over rho naught Cp lambda. Okay, so this is our height, thickness of the convective layer as a function of time. Okay, now you might be wondering why I have still kept qt as a and sorry, there is one mistake, and that is this has to be dt. Everywhere I have been writing that as so that should be dt, because we are integrating it with respect to time. All right, so that is now okay. So in the end also we can go and we can replace this with dt, 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 that is also dt. So this integral form for q with t I have kept, because assuming that q might not be constant. So this is if q is not constant in time. Okay, however, if q is q, which is basically the heat flux, flux is constant, then we can simply write h of t as a 6 qt over rho naught cp lambda. Okay, so this is the convective layer depth we get if q is constant in time. Okay, and based on this we can also get the temperature of the convective layer. That comes from this equation number 2, and that basically gives us T naught minus T naught plus 2 by 3 lambda h okay, so that will become T naught plus this 2 by 3 will go inside, six qt over rho naught cp gamma, and that gives us T as T naught plus eight over 3. I assume that is correct. Yeah, and there will be a gamma qt over rho naught cp. Alright, so this is the temperature you get as a function of time for the convective layer. Okay, so these are the parameters we wanted to derive. The thickness of the convective layer and temperature of the convective layer with respect to time. And you can see how the thickness is increasing with h is increasing with t to the power 1 by half, whereas t or delta t is also increasing with t to the power 1 by half. Okay, which tells you that it does not increase linearly, which we might think when it is a convective motion, but it works in this parallel behavior, and it is not. So let's say if that's your linear scale, then this should look something like this. Okay, so this is t to the power 1 by 2, either h or t, and this is your time. Alright, so now you understood how you can find the convective layer thickness with respect to time if you know the heat flux. So the parameters you need are heat flux, right, which you know whether it's function of time or just a constant, and then you need the rho naught, that is the reference density or density at the bottom of the fluid layer. Cp is the heat capacity, right, again that is of the air in this case, and this gamma is the stratification slope, which is there in advance, if that is already there before the convection begins, right. So if you know all these values, then you can predict the temperature and thickness of the convective layer for this sort of convection which we discussed here, right, in this atmospheric layer. But what we discuss can similarly be applied to lakes and oceans. So let me put them here. So convective layer in lakes or oceans. So in this case, as we discussed before, that if this is your water layer, right, and during winter or during night, heat actually releases from water into the atmosphere, right. So heat actually goes out in case of atmosphere, we assume that heat is coming into the atmosphere, right, from the surface. In case of water layer, we assume that the heat is getting released from the water layer, and that is why these fluid parcels that are there, they actually goes down. So convection happens downward rather than upward in case of lakes and oceans, right? And that is why in this case the density that we considered previously as in decreasing, or temperature which was increasing before in case of atmosphere, in this case the temperature here actually decreases. We assume that this is, let's say, Ti, where this was T naught, and T naught is the surface temperature, and T naught is greater than Ti. So as you go down, your temperature gets smaller and smaller, and that is why if this is your rho naught here, so your rho naught will increase as you go down. So if this is your rho I, so rho naught will be smaller than rho I. So as you go down, your density increases, right? And as you lose some energy from the water layer, for this green fluid, for example, they have become heavier because of losing heat, and that's why once they become heavier, they want to go down because of their density, heavier density. And that is why the analysis that we performed here, exactly same analysis will work, which we can simply copy. Okay, that is the formula that will work, and this will be the temperature profile. Okay, just one modification that you have to make is that while H is something that you are measuring from here, so this is Z equal to 0, and you are measuring H as you go down. So you can actually, if and you're defining this Z as your positive axis, so this H can be written as minus H, because your H value will be in negative, right, as you're going down. That is one thing. And also the other thing is this value will be negative, right, because your temperature as you go down is decreasing, not increasing, right? And that is when temperature is decreasing, that's why your density is increasing, right? And that is why these two modifications you have to make in case of lakes. So here you make minus sign, and this minus sign for height can obviously, or depth can obviously be adjusted depending on you define your axis to be upward or downward. But in case of temperature, you must put this negative sign, because temperature is actually clearly decreasing, and this does not depend on how do you define your axis, right? And that's why you have to put a minus sign, and everything else can remain the same. Okay, and accordingly, obviously, you have to find this rho I, which now decreases from, sorry, so that will go something like this. So Ti will be T naught minus gamma Z. The lambda Z, right? And because Z is negative, this lambda will still be positive, Z is negative, the whole thing will become positive. Or this is little confusing. Just give me a moment. So here also it has to be positive. This should not be negative. This should be positive, because Z is negative if you define Z to be vertically downward. Okay, so this is how you solve for convective layer in atmosphere as well as in lakes or oceans. And this tells you with time the amount of heat that is coming or getting released, how much will that affect the layer thickness, how much the layer will grow. And in fact, based on this formulation, you can predict where this layer thickness that you get as small h of t, is that going to be same as the capital H okay, of the lake or of the ocean. So in ocean it may not be possible because ocean depth is much greater, and that's why there is a chance that by the time you reach capital H, your season has already over, and summer has begun, right? And that is why this small h may never be equal to capital H for oceans, and likewise for atmosphere. But in case of lakes which are of finite depths or smaller depths, you may have smaller h to be equal to capital H, right? And this temperature, which affects the density and it also affects salinity and several other properties, they play important role in marine life and several other things that we care about. And that is why understanding the temperature behavior during different seasons and in fact daily matters a lot, and this formulation that we have derived may be used for those calculations.